Thank you for the opportunity to talk here. And yeah, I'm going to talk about representing clouds in large-scale models. And it's going to be a practical point of view of a person who happens to work in a group that develops one of such large-scale models. So why do we do that? Well, our climate projections are still very uncertain. This is looking at the projected surface temperature for one of the emission scenarios from the last IPCC report. And this uncertainty actually matters not only because we are curious about the science of the climate, but also it translates into an estimate on how much time we still have to act if we care about not crossing certain temperatures in the future. So why are we so poor at estimating how much time we have to act? Part of the answer is our lack of skill in representing clouds, especially the low clouds in large-scale models. And then why do we, so to drive this point, I'm showing a picture from my BOSS papers, and they grouped here the different large-scale models by how they predict the low clouds will change as we warm the climate, going from the left here, predicting the low clouds will be disappearing, to the right where we actually have some increase in the low clouds. And this uncertainty in the low cloud feedback is mapped into the projected warming due to the CO2 damping. So understanding the low clouds better would help us narrow down this uncertainty in climate projections. Why do we do so poorly with low clouds? This is a point that was also raised yesterday. We simply cannot resolve them in the large-scale models. So I'm showing here this range of scales from the grid resolution of the global model, which is a couple hundreds of kilometers, let's say, maybe 50 kilometers, through the scales relevant to the cloud formation, which could be of the order of hundreds meters, to the fine resolutions of, let's say, 10 meters that are needed to resolve those shallow stratiform clouds that we often have off the coast of California. And then, as we enjoy to appreciate in this crowd, the picture gets even more complicated when we consider the particles that are immersed in the flow. So here I'm showing example measurements for showing just the variety of sizes from tens of microns to a couple hundred of microns in size for the ice crystals. So you probably have seen this sort of argument before, but I'm actually going to take the time now to kind of walk you through this frankly dizzying range of scales that are needed to close the system and resolve the clouds in large-scale models. So I start with our subgrid scale model for the dynamics, so the scales that we cannot resolve in the climate model. And this is a software package that we use and develop that's called turbulence convection. So in this approach, we say the unresolved motions of air we'll try to represent by splitting our subgrid scale domain into two subdomains. One will be representing sort of coherent motions of air. Maybe you can think about them as convective plumes or updrafts that can lead to the formation of clouds. And then the rest of this unresolved dynamics will be represented by some sort of isotropic turbulence. So then we go through the process of coarse graining or conditionally averaging our equations of transport. So the Navier-Stokes equation overs those two subdomains, and that leads us to our solved equations. So we have our continuity equation where we look at how the mass of our coherent structure, so the plumes, is evolving. So the mass is the density of air times their area fraction, and it can evolve through the advection, through the mean flow in the horizontal and the vertical, as well as this closure that we need to say how much mass is being transferred from my coherent structures to the isotropic turbulence. And then I go through the same exercise if I want to know what is the scalar mean equation in my subgrid scale model. So this is an equation for the density times the area fraction of my subdomain, and phi could stand for any sort of scalar you're interested in. So it could be the moisture, like the total amount of water we have in the subdomain, or temperature, and so on. And again, I end up with my equations of transport plus the closure terms that I need for, again, the mass exchange between the subdomains, closure for the turbulent transport, and additional closures, which I mark here in orange because the cloud microphysics that I'm going to talk about is basically hidden here as one of the additional tendencies. And then I can go through the same sort of exercise for my isotropic turbulence, where I also want to solve for the covariance terms. So, for example, how my total amount of water is covariant with the temperature in the environment. Kind of similar, but progressively longer equation with, again, the transport through the mean flow, the mass exchange between the coherent subdomains and the isotropic turbulence. Even longer looking terms for the turbulent transport, my source terms from microphysics and other closures, and diffusion. So then how do we model the S for the microphysics processes? I'm kind of a little bit ashamed, or I don't know how to say it, to show it here, given the talks about the details of the microphysics processes from yesterday. But the answer is, unfortunately, we represent it in a very simple way. So we look at those particles that we know are in our clouds, and we split them very simply based on their behavior. So if they're solid or liquid, whether they follow the flow of air or whether they're sediment. And we end up with those artificial categories of cloud water, ice, rain, and snow. And then we only want to know what is the net effect of all the microphysics processes on the bulk properties. So maybe I want to know what is the total mass of cloud condensate, or what is the total mass of snow in my given grid box or a given subdomain. So in order to model such property, I need to assume something about the particle size distribution. So maybe it's an exponential distribution or a gamma distribution for each of those artificially introduced categories. And then I also need to assume something about how the properties of the particles inside each of those categories depend on their sizes. So for liquid spherical drops, this is very simple. We know how to model the volume or the mass of the liquid droplet. For more sophisticated shapes of snowflakes and ice crystals, this dependence could be modeled by some empirical fit to the data. And then if I want to know what is the evolution of, let's say, the mass of cloud water as is being depleted by the collisions with the rain, then I go through this simple exercise of saying it should be somehow proportional to the volume of the cloud condensate that is swept by my falling particles. So I have my cross-section area of my raindrop particles, I have my terminal settling velocity, and I do know there's more to it, the collisions, the turbulence, so I have some collision efficiency term that kind of encompasses all the different aspects of the process that we were listening about yesterday. And then I can integrate it and I end up with one of those closure terms for the microphysics. So then if I have some data, I could replace this term with some lookup table, let's say, that would be based on measurements or high-resolution simulations. But in the simulations I will be showing later in this talk, this is actually one number for each of the categories. So the collision efficiency, let's say, for raindrops interacting with cloud droplets is one number. Collision efficiency for snowflakes interacting with cloud ice will be another number. So that's how simple as it is in the model I'm talking about. So then this parametrization square problem is shown here in the equations, where I have my coarse-grained equations of air motion for my subgrid scale dynamics models, coupled to my simplified equations for the evolution of cloud microphysics. Or looking at it from the cloud microphysics point of view, my cloud microphysics scheme needs to know what is the variability in the subgrid scale of, let's say, the total amount of water or the temperature, so that I can sample the inputs better and as a result get better estimates of the total evaporation rate, collision rate, and so on. But physics and reasoning about equations can only get us so far, and in this coupled parametrization system, we roughly have about 23 parameters that represent the subgrid scale dynamics, the turbulence, and about 43 parameters that represent the different unknown properties of my very simple cloud microphysics scheme. So what can we do to actually solve this or to make the solutions better? Where in some circles, the answer is more data and machine learning. So that's what we're trying to do here, where I say my simple subgrid scale model, if it's not coupled to the whole large scale GCM system, it's actually very cheap to run. So I can run it multiple times for different sets of initial conditions, different cases, and look at my free parameters, so those 20 or 40 parameters, and see for which combinations of them I would get better fit to my observations. And then ideally those observations would be real-world observations such as satellite measurements or data from field campaigns. But in the examples I'm going to be talking about here, the data is generated also by models, just by higher resolution or more complicated models. So in this first example, I'm going to be showing, again, it's my subgrid scale model calibrated with large eddy simulation data to find better values of my free parameters. So the first example, I look at just 3 LES cases, and the cloud microphysics literature is full of LES cases that are designed to look at particularly challenging cloud types. So I'm looking at 3 of those, one for drizzling stratocumulus clouds, another for precipitating shallow convective clouds, and a third one for deep convective clouds, also with precipitation. So what I end up having is my end result, let's say, the data or the observations are the 3D LES simulations that I show here in the black line. And then the different colors showed the realizations of my subgrid scale model, so both the dynamics coupled with the microphysics. And then different colors represent the solutions either with different choices of how I formulate my sampling from the subgrid scale model to the cloud microphysics model, or by different calibration strategies, so different machine learning algorithms used to find the best fit to my data. So then looking at the skill, I have my cloud condensate profiles from my stratiform clouds, shallow clouds, and the deep clouds. In black, the dashed lines show the ice and the snow phase, and then the solid lines are the cloud liquid water, or precipitation here. So for the cloud profiles, I would say we're doing reasonably well as far as the subgrid scale models go. And then for precipitation, there's still maybe room for improvement. But this is still great result because we have one subgrid scale model that unifies all those different types of clouds and one cloud microphysics scheme with one set of free parameters that gives us all those different cloud behaviors. But I think other people will be raising this point too. We don't want to lock ourselves into those individual test cases. We don't want our scheme to only do well for RICO-like looking clouds. So while I struggle with cloud microphysics, and other people in the team I work at are expanding this idea of generating artificial data to calibrate our schemes. So here I show an example where we have a library of large eddy simulations that are forced by the global climate models. So we can generate those artificial observations for different climate conditions, for different seasons, and we can target them at the areas where we know we do the worst. So as I mentioned, we do very poorly with low clouds. So we can spin our LES simulations in those regions where, for example, here, this is the region, let's say, off the California, where we have those stratiform clouds that have high cloud fractions, and then we can kind of sample this transition from stratiform to shallow convective clouds with our LES simulations, and then use this library of LES simulations to further improve our scheme. I'm not going to show the results from that because the thing I want to mention is that this approach for generating artificial data to then constrain our subgrid scale dynamics is great for the subgrid scale dynamics model, but for the cloud microphysics model, which is the thing that's closer to my heart, we're still not really resolving the scales. So in the simulations I was showing here, the LES model and the subgrid scale model were actually coupled to the same cloud microphysics scheme, this very simple bulk scheme that I've shown before. So maybe I'm improving my representation of mixing between my coherent sculptures and the isotropic turbulence, but my rain evaporation rate will be as poorly represented here as it is here. So we need to have some sort of substitute for this data generation machine if we want to improve the microphysics as well. So I'm going to argue that such a representation of truth could be the Lagrangian particle-based methods that we can then use to constrain our simple bulk schemes. So the Lagrangian particle-based methods are, I would say, maybe in spirit or in aspiration, somehow similar to the results from the DNS simulations that we have seen yesterday, in the sense that they model the actual size distribution of particles by tracking individual particles in the computational domain. So we know what is the location, the wet and the dry radius of our particles, their chemical composition, either through the parameter, the hygroscopicity parameter kappa, or maybe through the tracking mass of individual chemical compounds that are dissolved in the droplets. But those methods are designed to actually work in the LES configurations. So they are designed to work in the simulation that spans a couple of kilometers and in grid boxes that span a couple hundreds or tens of meters. So in order to make them computationally tractable, we also introduced this multiplicity parameter that basically governs how many real-world particles are represented by one simulation particle. And in the LES applications that span, for example, the size distributions from aerosol particles to raindrops, this multiplicity can be of the order of thousands of millions of real-world particles represented by one computational particle. But as I'm showing here for one of our test cases, using such methods, we can actually evolve the size distribution of, in blue shown here, the cloud and precipitation particles without assuming anything about the size distribution. And another example here, where I'm showing here the aerosol particle size distribution, initial condition in black, and then resolved by particle-based methods, where I'm showing here how the size distribution was changed through the collisions and also through the chemical reactions. So to finish up, we're now trying to recreate the success story of the calibrating the subgrid scale dynamics with LES by calibrating the cloud microphysics with the Lagrangian particle-based simulations. So the library we're building right now is based on a one-dimensional setup where the clouds are being formed in prescribed temperature conditions with some pulse of velocity that transports the moisture from the surface, which leads to the formation of clouds in this very simple modeling setup that can later evolve through the microphysics processes. So this is an example of such library of simulations where the Lagrangian methods evolve this system differently based on different initial conditions for the number concentration. And then we can try to, calibrate our microphysics schemes. So here in blue, I'm showing the Lagrangian microphysics scheme simulation, and then in the different colors, I'm showing the uncalibrated versus the calibrated bulk scheme that tries to mimic the solution to the system. So to finish up, I'm gonna use the slide with different software packages to kind of underline that this whole development effort of building a better climate model is a software effort that is spread among many people. So when I was talking about the subgrid scale models, I was talking about the cloud microphysics and the turbulence convection package that we're developing. When talking about the calibration methods, I was talking about the ensemble Kalman processes and the pipeline for the calibrations. And then the microphysics scheme is used in the simpler setup. So this is all developed at Klima, at Caltech, and in Julia. And then the Lagrangian particle-based schemes that I'm using for calibrations are developed at Jagiellonian Institute and are implemented in Python. And with that, I'm gonna wrap up and answer any questions.
We're open for questions and discussion. Yeah, Eberhard.
I just leave it on. So my question is, what would you need? I mean, if you do deep learning anyway, and you would get experimental data, I mean, what would you actually need to learn what you need to learn? You know, what if I would be a magician, you know, I say zip, and there is all this experimental equipment, what would be the minimum requirement that you would say that's useful?
I think.
I mean, anything is useful, but
what he's saying is, if he was a Max Planck director and had
exactly.
a lot of money,
no, I'm thinking bigger. I'm actually thinking
measure?
bigger. You know, I mean, if you all, you know, team up or something, and we decide to throw our energy on some specific problem and just say, let's nail that one, what would it need?
Right. I think two answers. Maybe one is going through this hierarchy of different models. So, with such a simple bulk scheme, I can't really capture any of the measurements that you were showing. So it would have to be some sort of hierarchy where I start with measurements, then use some higher resolution model, maybe the microphysics scheme, like representation Lagrangian microphysics, or maybe DNS simulations to kind of capture the, let's say if we're talking about collisions, then maybe that would lead to a better representation of the collision kernel.
Pollution.
Pollution?
No, what was the word?
Collisions.
A collision kernel.
Like collision kernel, okay. Right? So then I would have a better understanding of how this collision kernel is formulated by trying to machine learn or to fit the Lagrangian microphysics solution to the observed measurements, which I could then.
So would you be able to classify in some sense, what are the, I mean, looking at all clouds and looking at all situations might be a little bit much for experimentalists to do.
Right.
But you could say, these are the typical, like, what Björn Stevens says, we have to go to the trade wind region and look at these clouds, for example, and then we nail trade wind clouds, or because they're very reliable, they always do the same thing, but you could also say other things are much more important, like, ice, mixed clouds. I don't know. I'm just, if you have, X amount of equipment, what would you invest it broadly, or would you say, let's focus now from your wish? If you would have a wish right now and say, I would really like to know that part of the corner of this huge phase space better.
Yeah, I think
which corner would it be?
I think the ice phase. Like I was focusing more on the low cloud,
ice.
But I think the ice phase clouds are like here. I was more focusing on the challenges that are needed to formulate those schemes across the different scales. But as we were talking about yesterday, there are still unknown gaps in actual understanding of the physics, and more of those gaps are located where the ice phase is.
With the ices, yeah. Okay.
I think.
Thank you.
Thank you, Anna. Very nice talk. I was wondering, so of course, what you have as your ultimate goal is you want to use models like these in order to make long-term climate predictions and so on. Given the scale of the entire atmosphere, that's of course very challenging. But I was wondering if you can take smaller elements of your model and use those in order to assess the efficiency or efficacy of certain geoengineering models that have been proposed. So could you take your model, for example, to see what would be the effects of injecting some aerosols into the atmosphere, or what is the effect of having additional volcanic ash in the atmosphere on the evolution of clouds at a smaller scale?
Right. I think we could try, but we would probably have to ramp up our bulk scheme microphysics before we can do that. Otherwise, with the simple formulation I have shown here, we can't really model the aspects of how the number concentration is changed by the geoengineering plans, let's say. But in theory, we could, for example, set it up similar as with this library of simulations, right? Where we maybe first force our LES simulations with the data, or trying to represent the question you're interested in, and then use them to calibrate our subgrid scale model in a way to best capture the process, and then plug it into the actual large scale model to see the net result. But
because it seems like people are getting very serious about these efforts, doing large-scale geoengineering, and so we have computational tools and models that help us, get an idea of how effective those models might be, or what kind of unintended side effects might come up. That will be very useful.
Yeah, I'm happy that people are interested in it, because I think it will lead to great science. I'm not sure about the actual application, maybe.
Okay. Thank you.
I'm really impressed by this talk and by the, Michel Louis from Cornell University. I'm surprised about one thing though. what about radiation? I mean, at the end of the day, this whole thing is coupled through radiation, and that's what we're trying to
Right.
Avoid trapping, I guess.
Yeah, so radiation would be, I guess, ideally it would be coupled through the subgrid scale model here. So given my cloud microphysics closure, and given, maybe I'll go to the scalar equation. So given my cloud microphysics closure and given the equations I'm solving for my scalars, I would be able to say what is the cloud fraction, let's say, in my subgrid scale model. And then that could then be coupled to another closure, which would say, yeah, how I interact with radiation. Yeah.
There's time for another question. Yep. Oh, sure.
Hi, Roy from the Eckert-Meiber group. So the way you basically do Bayesian statistics on this thing is not by assuming any prior on the parameters or anything, or do you?
Yes, not really. I mean, I assume something. So let's say with some of those parameters, I know they should be within certain range. So my prior is usually just a uniform within certain range. And then the range, yeah, sometimes it's based in actual understanding of physics, and sometimes it's just our best guess of, given what is currently used in the models, then, I don't know, plus minus this.
Right, yeah. So, but you didn't show here the uncertainties of the posterior. Right,
so we have different ways in which we sample. So in one of the approaches, the way we sample, our free parameter space kind of collapses very quickly to the actual solution. So you get the value, but you don't really get the distribution. However, we have another algorithm where the way you sample actually forces some of those particles to like remain further apart from the actual solution, and that gives us some sort of estimate of the...
Where the actual solution is the LES.
In here, in here right now we are calibrating to the LES. But yeah, we have a way to calibrate. I don't know if I have... I might have deleted that one. Yeah, I can show later. We have a way to try to estimate the uncertainty of the parameters, like the free parameters as well. But yeah, it would be based on the LES comparisons right now.
Yeah, okay. So thank you.
Yep.
Okay, I mean, maybe just a quick editorial comment. I think what the Klima collaboration, Anya and her collaborators are doing is really, I would say, intellectually honest. Climate modeling is incredibly challenging and almost depressingly challenging, right? But I think this idea of just starting from scratch and building a model where you really expose all of the uncertainties to the community is pretty impressive.
So yeah, and maybe I can say like all the code development is done on GitHub. So if you're interested in how we fail at different things, there's a history of
it's very
review
open.
Commits and bug fixes. So yeah, find us on GitHub, I guess.
Yeah, it's really good. Okay, thanks a lot. Let's thank Anya again.